All right, it's recording. Here we go. Last exercise of chapter 13. It is expected value, variance, and standard deviation, some of which you may already understand, some of which you may not. So today's lesson is me describing what those terms mean. Expected value, which we use a capital E, as you can see in the notation there. This capital E means expected value, and the expected value is essentially the mean or the average. It's just that it's what you expect in the long term. So overall in the casino, I expect that they're earning profits than losing. If you play in the long term, you're more likely to lose. That's what I expect, right? So the expected is actually just finding the average, which means over the long term, what does it tend towards? The formula here, this means sum. Whoops, let me just do that again. Oh, it's a bit laggy today. Very laggy. Okay. This means sum. So it means you add all. Now remember yesterday I taught you the x random variable, and it can take little x, which is the possible outcomes of your discrete variable, or it could be a continuous. In this case, it's discrete. This is your possible outcomes. And you're multiplying that to the chances of that outcome occurring. So chances. Okay, so usually the average, when you calculate the average, the way you do it is you do it like this. Average of anything is the sum of all numbers divided by the number of numbers. Right? So why is it the sum of all numbers divided by number of numbers end up being x times the probability? So you can either memorize it or you can understand where it comes from. So that's what I'm showing you today. I'm showing you why this formula works, and then you just need to know how to use it. Now every chapter, chapter 13, chapter 14, chapter 15, chapter 16, they use the same theory, but by using the same theory, they come to a new rule. So for example, in chapter 14, E of x ends up being the number of trials times the probability. Okay, so then if you do chapter 15, there'll be a different one for continuous. So you just need to know what type of data or probability do you have, and then you apply the right rule. That's the only difference. But the theory for what does expected mean, what does variance mean, and what does standard deviation mean, it's all the same. It's chapter 13, 14, 15, 16, 17, it's all the same. So your goal is to know the difference between each chapter. Yeah? So let's now start. So we know the average is now E of x. That's the notation for it. That's the formula. X values times the probability. So here's an example. Say I give you this probability distribution. We don't know what x currently represents, but we do know the possible x values are 0, 1, 2, and 3. So it could be that I've rolled the dice 3 times, and x random variable, I might be interested in seeing how many times do I get the number 2. I either get, out of those 3 rolls, I get 0 2s. I get 1 2, and the rest is not 2s. Boys, can you stop? Or you get 2 2s, or you get all 3 2s. These are the chances of them occurring. So if I want to know what's the expected, or what's the average overall, if I rolled the dice 3 times in the long run, what would it tend towards? Would I get 2 2s on average, or would I get 1 2 on average if I rolled it 3 times? Based on whatever this random probability distribution is telling me. So it's telling me I've got 6% chance, roughly, 6.4% chance of getting 0 2s. I've got 28.8% chance of getting 1 2 out of the 3 rolls. I'm just making up the scenario so that you can read what the table means, yeah? It doesn't have to be 2s. So what is it tending to? Now you can sketch the distribution on your CAS, and then you can kind of predict roughly where the expected is, or you can calculate it. Yeah, so if they give you a graph, you have to learn how to read a graph, which is D. Whereas this one, you're actually doing the calculations for it. Yeah. So C and D is about distribution and then calculation. So here, how do you do the calculation? Is literally x multiplied to the probability. So the first one is 0 times, what's the chances of getting 0 2s in this example? 0.064 plus, what's the next one? X is 1, so what's the chance of getting 1 of the observation that I want? Well, the chances are 0.288 plus 2 times. So this now is 2 times, I've got 43.2% chance of getting 2s, and then getting all 3s, then that would be 3 times 0.216. So you do that on your calculator, and if it's in exam 1, they'll give you numbers that you can easily do. Okay, so in this case, what does that end up being? Anyone got a CAS ready for them? Let's type this up. It's 1.8, was it? Let's do this. 1.8. Let's see. 0 times 0.064 plus 1 times that, which is 0.28 anyway, plus double of that, so 2 times 0.432 plus 3 times 0.216. Was it 16? Yeah. Oh, what did I do wrong? Thank you. 1.8. So what does that mean? So getting 1.8 is one of the answers, but the interpretation of what this means. What does 1.8 mean? In the scenario that I made up just now. Rolling the dice 3 times. Observation is, I'm looking for 2s. So what does 1.8 mean? Yeah. So on average, in the long term, I expect that I will get just less than 2 2s in 3 rolls based on the percentages that they've given us there. That's roughly where I expect. So when you roll it, I know that there are more chances that you're going to get 1, if not possibly 2. That's what I know. Okay, so based on that, that's what the average means. And that's what essentially when you do, gambling and all that, the casinos are looking for on average, what are you getting? Now, why does that work? So we know averages since primary school. We know that it's sum of all numbers divided by number of numbers. So why is this rule finding the average? So here's an example that sometimes in your textbook will get you to do. I want you to read this example and see if you can fill out the distribution table. So I'm going to try to give you hints, but you're going to have to figure out what the distribution is. Yeah. So here, a person, so let's say you buy a lucky ticket for $1. So you buy a ticket for $1, and then they tell you, well, you actually know that there's 20% chance of you winning $2. Then you have a 5% chance of winning $11. I should do it color-coded, actually. I'll do it color-coded. $2 is 20% chance. And then you've got otherwise you lose. Now the question is asking you, how much could you expect to win or lose per game in the long run? So clearly we're finding the average in the long run, which is the profit or loss. Let X be the amount that the person will profit. So I want to know how much they will profit from each game. Okay, so let X be the random variable if you had to calculate the profit. So think about it. You got scenario 1, you either win $2 and you spend $1 to buy a lottery ticket. Or scenario 2, you spent $1 to buy a ticket and you win $11. What's your profit? Or otherwise you lose. Fill out that distribution table. So the possible X values are, what are my possible X values? Anyone know? Beautiful. So you either lose, so you spent $1 and you lost it, so hence you lose $1 overall, or you gained $1 because you won $2 and you spent $1, so you gained $1, or you won 11, which means you gained $10 profit. So -1, 1, and 10. Very good. Now, what's the probability for each one? 0.75. Oh, yeah, sorry. That's right. 75% chance for otherwise, and this one was 20% chance of 0.2, and this one is, what does it say? 5%, 0.05. All right, that's filling out the distribution table. So the possible values discrete. You either lose 1, gain 1, or gain 10. You've got your percentages. Now, normally, because you know the rule, you can actually calculate it by just doing -1 times 0.75, plus 1 times 0.2, and 10 times 0.05. But I'm interested in why does that work. So here's an example. I said, let's say we play 1,000 games. Okay, so you had 1,000 trials. Then, according to the average, 75% of those 1,000 games, you will lose $1. So what's 75% of 1,000? 750. But how you would have done it is you would have done 0.75, which is 75%, times the 1,000 games, which you know is 750 games. Yeah, so that's how many games that you would have lost $1. So if you think about it, to find the average, you're doing -1 plus -1 plus -1 How many times? 750 games. So you don't want to sit there and write -1, -1, -1, -1, -1. So instead, the quicker way is 750 games times -$1. True? Okay. Plus, how many games or how many dollars can you actually win for a profit of $1? Well, 20% of the 1,000. But what's 20% of 1,000? What's 20% of 1,000? 200. So in this case, same thing again. You would have done 20%, which is 0.2, times 1,000, and that gives you that 200 that you want. But then you would then times that by 1 for the dollar, because it's $1 plus $1 plus $1 plus $1 plus $1, summing all the numbers, $1 plus $1 for 200 times. Then you do plus, you got 10, to get $10, it's only 5% of it. So 5% of, so this was 20%. The 5% of the games, 5% of the games was, what's that? 5% of 1,000 is, what does that work out to be? 50. Yeah, so 50 games. So 0.05 times 1,000. That's 50 games there, and you're timesing it by 10. Now, what you notice is that's the sum of all the numbers. So your total profit, which is based on what you sum to, divided by the number of games you have. Now, how many games or how many numbers would you have had if you added 750 negative ones plus 200 of those $1 plus 50 of those tens? There's a total of 1,000 games, right? So it's all out of 1,000. But can you see in the mathematics in itself, had I not wrote the working out, and I just wrote 750 times -1, 200 times 1, plus 50 times 10, it misses out on the fact that you can see the working out here. They're all dividing by 1,000, and they all have a factor of 1,000. So that means you're always going to cancel them out. No matter how many games you play, the average will always cancel out. That's why it ends up being, it's just 0.75 times -1. So right there, this is where probability of the event times the x value. Probability of the event times the x value. Probability of the event times the x value. Because you don't need the 750, you don't need the 200, you don't need the 50. The 750 and 50 is all arbitrary because it's dependent on the games. So if I played 10 games, then that would have changed. That would have been like 7.5, 2, and then 0.05, or 0.5, right? So because of that, you don't actually need the number of games. You just delete that. And all it is just probability times x. That's where it's coming from. Okay, so that's why whether you do 100 games or whether you do 1,000 games, it will still end up being the same. But the answer is a loss if you actually work it out. Anyone worked it out so far? What's the profit or loss? So 0.75 times -1 plus 0.2 times 1 plus 0.05 times 10. What'd you guys get? And that implies that you lose 5 cents in the long run for every game that you play. Okay, so for that particular scenario, you know that in the long term, you'll just be losing every game you play, but there is a chance that you might win. Okay, but in general, that's how casinos work. They already know in the long term you're losing. They've already worked it out. But when you read it, it sounds pretty cool. $1 and you might earn $10, even though there's a 5% chance you're like, I could be the 5%er, right? But every game that you play, you're losing a certain amount. Yeah. All right. So that's why the expected value works. Now let's flip over and let's do just the rules so that you know how to work with the rules. You can look at the proofs and all that later on. At the moment, you just need to know how to use the rules. Let's flip over. There are some key properties I want you to highlight or box. This will be useful in your bound reference. I don't think some of it is in your formula sheet. That's why. So what's useful? I'm going to highlight them. This is useful. This property gets used for the proofs. For every chapter, 13, 14, 15, 16, if you want to know where the formulas come from, it starts off there. Okay, so likely you'll need one of that. Or the one I just did above here, they'll use that theory there. That's where the proofs generally start. Okay? But we're not doing special, so you don't need to know how to do the proofs. You just need to know how to use them when the question's asked. Okay, that's one of them. You need to know this one. So that's the one I just showed you. That's to find the average. Then another one is variance. I'll describe what variance is theoretically, okay? So the two key formulas that you'll use, this is the proof. So if you want to know where the proofs come from, that's where it starts. This is the one you do on your calculator. So we call it a computational formula. That's the one you use on your calculator. And this is when they start to change things. So in the exams, you can expect this one. So the variance of AX plus B and the expected value of AX plus B. Maybe I'll do it in green so that they look similar. That in green, that in green. And I'll just delete that. Okay. So one's theory for proof. Maybe I'll do that blue so you can see the relevance. This is blue. So theory. In theory, computation. Technically, that is also computation as well. Yeah, I know. That's true, because the other symbol, yes, Joe is correct as well. Mu is also the symbol for expected value. Okay. All right. Now, let's give you a sort of a definition of what variance versus standard deviation is. Most students just know variance is that symbol there, sigma squared, and standard deviation is sigma, right? Now, out of these two, they are related and they do matter. Okay, one is squared and then one is not squared, and there's a reason why one is squared and one is not squared. Okay, the filling in the box here, this is average. What is the variance when we say variance? It's the spread of the data. So your data can be very wide apart or it can be close together, and it tells you things about the data. But the average is not the average of just how spread the data is. It's actually the average of the squared difference. Now, this is what I mean. Why do we do the squared and why do we do the difference? So here's a logic. Let's say I'm a really good methods teacher, hypothetically. I'm so good that I can predict with a model. I've got some mathematical equation that I can literally predict from day one you come in. I can predict what your eta is going to be. Okay? Let's say I predict your eta to be this line. This is your eta prediction. Okay, so that's my eta prediction. And all I need to know is how many times you eat in the morning. Okay, let's just say you eat once, twice, 3 times, hypothetically. Okay, and I'm able to tell. So if you told me you ate 2, I'm like, great. Actually, how many times do you eat in the morning, Joe? Do you eat breakfast? No, so he's 0. So I'm like, so your eta, I'll be like 50. All right, let's just say that. Let's just say my calculation was so on point, I think anyway. This is the actual data when I actually get it. So I made a prediction. That's the prediction. But the reality is that you guys go into the exam, you're like, I'm going to prove Mr. Tran wrong, and I'm going to eat nothing for breakfast, and I'm going to show him I'm going to do better. So Joe goes to the exam, and he actually does get an eta much above what I think. Let's say the others, let's say all our other students in our class, see the spread of the data that I'm doing? Now what you see here is, you see, these are called your X datas. Every student is an X data. The mean is what I expect you to be. So this line is the expected. I'll do another color. This is my expected. So every point, I have an expected answer for you. So for Joe, I had an expectation on where he was going to be. This is my expected. So that's my mu, right? So everyone has an expected one. But the difference between my prediction and your actual score, so the actual score that you got, minus my prediction, that will tell how far I'm off. Because if I predicted you're going to get 50 and you got 50, that means I had 0 error. True? So the question is, what did you get? So let's say you got an 80 eta and I predicted that you're going to get 50 and it's out of, what's the, don't worry about the, just minusing it for now. Okay, don't worry about the probability, but let's say 80 minus 50. So how far off am I in terms of the prediction for his eta? 30, right? So this is 30. But here's the problem. I could have said the same for someone else that I could have said, let's say, Ryan. I could have predicted, Ryan, how many times do you eat in the morning? Give me a big number. 7 times in the morning, right? He eats 7. He's off the charts. I'm like, for sure, he's going to get 99 is what I'm guessing. But it turns out that in the exam, because he was so confident with my prediction, he does no studies. He ends up in the exam, Ryan now gets, let's say I predicted that he was going to get 99, but then he gets 69. if we find the difference, how far off am I? How far off am I now? Negative 30. Now here's the problem. Do you see the problem? I'm equally as wrong for both of you. But if I found the average, let's say I only had those two in my class, and we have to find the average, it's the sum of numbers divided by number of numbers. The problem is 30 plus negative 30 divided by only 2 students in my class. The net sum ends up being 0. But what does 0 mean? That implies my prediction is really good. I have 0 error. But the reality is, what's my error? It's 30, right? I'm actually off. But the problem is that when you do the subtraction, when you do the difference, there's a negative version and there's a positive version. This is why when you do the variance, you see the formula is actually saying the same thing as what I just described. They're actually asking us to do the expected, this is the actual value, minus your prediction. Why do we square it? Because if I square it, I get rid of the problem. Both of them will be 900. But what's the problem if I square it now? If I square it, and then you say, my error is 900, I'm like, how do I even get an error of 900 when the h is only up to 99? So the problem is when you square it, see the average of my error, if I don't square it, you can't do the comparison because then it'll be wrong. So when I square it, yes, it tells me the spread correctly, but it's inflated. You make me look so bad with my prediction when I'm only 30 off, but 30 is pretty huge too anyway, right? So that's why standard deviation is exactly the same thing. Standard deviation was the square root. Because if I squared it to 900, but if you square root it now and you take the absolute value, it's 30 again. That's why standard deviation tells me the spread, but actually tells me the spread according to the units. This one doesn't. Because once you square it, you square both of it now. I am equally correct. It is 900, and it's much better. It is equally correct wrong, that I am wrong by 900, but the 900 is an overinflated error. That's why we got to root it. And that's why standard deviation is called the square root of variance, even though both of them mean the same thing. They find the spread of the data. And that gives me 30. So that's a better accurate measure. So if I find the average, so the expected value using standard deviation, it's much better. Okay, so that's the theory. Do you need to know that in detail? Not really. You could get by. But if that made sense to you, fantastic. Otherwise, you can just memorize the formula and just follow on. But that's why this is the theory. And then every other formula that you go from chapter 14, 15, 16 follows from that theory. Okay, and that's how these two are linked. Cool? All right. So in a nutshell, if I confused you just now, don't worry, move on. Just take on the fact of what I highlighted. Those are the things you need to know. So, what do you do in this exercise? Here we go. Example 2. I'll do this example and then I'll get you to practice the next one yourself, or you can work on the exercise. But it's the same idea. You're using expected value formula, variance formula, and then standard deviation once you know the variance. Yeah? So here we go. I've given you something a bit tricky. I've given you now not just the variance of x, but I'm giving you variance of 2y minus 1. So that means I want you to use this one, because that's what examiners will do. Okay, so I want you to use the green one. So the green one says, if you have a linear function, instead of just the x random variable, what if it was a linear random variable? So that means the coefficient of a becomes a squared, and then the b doesn't matter, and it's just times the variance. So you still need to find the variance of the data. Okay, so here we go. Let's do this. First thing, to find variance of 2y minus 1, looking at the formula. Remember the formula was, if this is ax plus b, then the formula was a squared times variance of x, right? So that means you're writing so far 2 squared, which is 4. I'll just write it like this. 2 squared times variance of y. So at the moment, I don't know what the variance is. Okay, so this is your ax plus b. I'm just using the formula. Okay, so at the moment, I need to find this. This is what I don't know. 2 squared I do know. That's 4. How do you find variance of y? So you go back to the formulas that I've given to you. I've given you the formula. You've got a theoretical formula, and you've also got a computational. When you get to this step, do the computational. If you have UDFs, there is apparently one that you just type in the probability table. So you do 0, 1, 2, 3, 0.3, 0.2, 0.3, 0.2, and it does your expected value, your variance, and standard deviation all in one go. Saves you a lot of time. Okay, so worthwhile if you haven't looked at UDFs. The one I put on OneNote somewhere was the UDFs. Yeah, just down there it says CAS UDFs. If you need it, I can pass it on to you. You can start practicing it. But there should be a probability one where you literally just type those 8 digits and it'll do the rest for you rather than you doing by hand. Okay, but let's do it by hand because I haven't practiced the UDFs. I just know you can do it. Pat does it a lot. So variance, what's the computational formula? It is E of x squared. Okay, so rather than your x variable, now you have to square all the x values first and then find the average. Minus E of x all squared. Okay, looks scary, but it's not that scary. Okay, so one is what we did before, find expected value, okay, and then you square that number. The other one is you have to square the x's first and then find the expected value. Yeah, so here we go. Let's find the expected value the way we did just then. So E of y, so I should change that to a y to make it match. E of y squared, E of y, okay? Here we go. So our probability table, to find the expected value, it was y times the chances, so 0 times 0.3, plus 1 times 0.2, plus 2 times 0.3, plus 3 times 0.2. Someone work that out for me. What does that equal to? I mean, that's what? 2, 6, and 6? So 1.4, is it? Is it 1.4? Yes, it is 1.4. Yes, you're right. Yep.
When do we get our bad references back?
Continue recording. But UDFs, you can go onto my OneNote. I've got the PDF there too. If you want, I can send the stuff to you too, so you can do it. Yeah. All right. Now the question is, how do you do E of y squared? So a lot of students get scared when they look at that computational formula. We just did this one before. We know how to do that one. So that's just x times the probability, or in this case, y times the probability. This one literally just means square the y's first before you find the average. So that means instead of 0, it's 0 squared times 0.3, plus 1 squared times 0.2, plus 2 squared times 0.3, plus 3 squared times 0.2. That's what it means. So at the end of the day, the variance is this one, take away that one. Okay, this one, take away that one. So here we go. So we got 1.4 for this one. Let's work out the next one. I'm going to do it on a CAS calculator here. So 0 squared times, actually I don't even need to do 0 squared because it's going to be 0. So it's 0.2 plus 4 times 0.3 plus, what's the next one? 9 times 0.2. 3.2. Okay, so we got 3.2. So that's my E of y squared. So my variance of y should equal to 3.2 take away 1.4, which is 1.8. There we go. So we now have variance of y. So to answer the top question, since this is now E of y, so 3.2, maybe I'll do it in red. 3.2, take away 1.4, and we've got 1.8. Then that means this one, which we said before was 2 squared times variance of y, which becomes 4 times 1.8, which is what? What's that? 4 times 1.8, 7.2. So this is variance of 2y minus 1. That's your variance. Then to find standard deviation, if they ask for standard deviation of 2y minus 1. Which one? Oh, did I not square it? You're right. Sorry, I didn't square it. So it's all wrong now. Damn. It was a square. 3.2 take away 1.4 squared. 1.24. Thank you. 1.24. 1.24. 4 times 1.24, 4.96. There we go. And that one should have been, no, we don't need to write that. Good, yes. There we go. Because if you think about a spread, let's do a quick distribution. The 2, if you think about what you're actually doing, it's a transformation. It's just moving to the right or left. So you just shift the spread. But the variance, the spread is still by the dilation. All right, and that would just be the square root if you're finding standard deviation. But that's how you do the technique. So you learned expected value, you've learned variance, and standard deviation is just the square root of that. That's what you're practicing in the final exercise of chapter 13. The back questions are problem solving. You can have a go with these ones. So this one, they're doing a reverse. They tell you what the variance is. And you have to work backwards to find K. Have a go with that one. And same thing with this VCAR question. Random variable X has this probability distribution. It's kind of like what I did yesterday, except they've got variance there as well. See if you can answer those questions. You've got UDFs. Maybe see if you can answer variance there with the 3, but it's a 3 marker, so you probably have to do it by hand. Okay, you have to do that by hand there. All right, team, I'm going to stop the video there. That's 31 minutes of me talking, but hopefully you understand a bit more about the probability component.